August 29, 1907. The St. Lawrence River, Quebec, Canada. At 5:37 p.m., the south cantilever arm of the Quebec Bridge, a structure designed to be the longest cantilever span in the world, twisted, buckled, and collapsed into the river in 15 seconds. 19,000 tons of steel fell like a house of cards. 75 men died, most of them crushed or drowned as the wreckage hit the water. The disaster was not caused by weather, sabotage, or material defects. It was caused by one man's arrogance, one calculation error, and the refusal to admit a mistake until it was too late. The Quebec Bridge was conceived in the 1890s as a solution to a fundamental problem. The city of Quebec sat on the north shore of the St. Lawrence River, one of the busiest shipping channels in North America. The river was over 3,000 feet wide at this point, far too wide for a conventional suspension bridge using the technology of the era. The only viable design was a cantilever bridge, a structure where two massive arms extend from opposite shores, meeting in the middle with suspended central span. Cantilever bridges were not new. The fourth bridge in Scotland, completed in 1890, proved the concept worked for long spans. But the Quebec Bridge would be different. It would be longer, more impressive, a symbol of Canadian engineering prowess and national ambition. The original design called for a main span of 1,600 feet, which would make it competitive with the fourth bridge. But that was not enough. In 1903, the chief engineer of the Quebec Bridge Company, Edward Hall, revised the design to 1,800 feet, making it the longest cantilever span in the world by a significant margin. This decision was driven by ego, not necessity. The engineering challenge was immense, and the man chosen to oversee it was Theodore Cooper. Cooper was not just any engineer. He was a legend. Born in 1839, he had worked on some of the most famous bridges in America, including the Eads Bridge in St. Louis, the first major steel bridge in the United States. By 1903, Cooper was 64 years old, semi-retired, living in New York City, and suffering from chronic health problems that made travel difficult. When the Quebec Bridge Company offered him the position of consulting engineer, he accepted with one condition. He would have absolute control over the design, but he would not visit the construction site. All decisions would be made from his office in New York, based on reports and telegrams from the site engineers. This arrangement was insane. A bridge is not a theoretical exercise. It is a physical structure built in a specific location with specific geological conditions, weather patterns, and construction constraints. An engineer who never visits the site cannot understand these factors. But Cooper's reputation was so towering that no one dared question him. The Quebec Bridge Company agreed to his terms. Construction began in 1905. The design was a cantilever truss bridge, meaning the structure consisted of massive steel frameworks extending outward from piers anchored to the riverbed and shore. The bridge would have two main cantilever arms, one extending from the south shore and one from the north, with a suspended central span connecting them. The key to a cantilever bridge is balance. The weight of the extending arm must be counterbalanced by the anchored portion behind the pier. If the extending arm is too heavy, it will pull the entire structure into the river. Cooper's design called for the south arm to weigh approximately 12 million pounds when fully extended. This weight would be supported by massive compression cords, steel beams running along the bottom of the structure, and tension cords running along the top. The compression cords would bear the primary load, resisting the downward force of the cantilevered arm. The calculations for these loads were done by hand using slide rules and logarithm tables. There were no computers, no finite element analysis software, no automated stress calculators. Every number was calculated manually, checked manually, and recorded manually. Human error was inevitable. The critical mistake occurred during the design revision in 1903 when the span was lengthened from 1,600 to 1,800 feet. Lengthening a cantilever bridge is not a simple matter of adding more steel at the ends. The entire load distribution changes. The bending moment increases exponentially with length. A span that is 12.5% longer does not require 12.5% more strength. It requires significantly more, potentially 30 to 40% more, depending on the geometry. Cooper lengthened the bridge but did not fully recalculate the weight of the additional steel required. He made an assumption. He assumed the weight increase would be proportional to the length increase. This assumption was wrong. The actual weight of the extended structure was approximately 8 million pounds heavier than Cooper's calculations predicted. The bridge was being built to hold 12 million pounds. It would actually weigh 20 million pounds. The compression cords specified in the design were inadequate. They were too thin, too weak, and would buckle under the actual load. But no one realized this because Cooper never visited the site to verify the construction matched his assumptions. Reports from the site engineers were optimistic and vague. Progress was on schedule. Everything appeared normal. In reality, the structure was doomed from the moment the first steel beam was erected. By August 1907, the south cantilever arm was nearly complete. The structure extended over 900 feet from the shore, a massive latticework of steel towering over the river. It was an impressive sight, a testament to human ambition. It was also unstable. The compression cords, designated as members A9L and A9R, were beginning to show signs of distress. These were massive steel beams, each over 3 feet in diameter, running along the bottom of the cantilever arm. They were designed to resist compression, to bear the downward load without bending. But they were bending. Norman Mucklow, the head riveter on the bridge, noticed it first. Mucklow was not an engineer. He was a skilled tradesman, a man who spent his days working on the steel itself, driving rivets, connecting beams, and observing the structure up close. In mid-August, he noticed that the compression cords were bowing outward, bulging slightly in the middle. He measured the deflection and found it was increasing daily. On August 20th, the deflection was 1 inch. On August 22nd, it was 2 inches. By August 27th, it was 3 inches. This was catastrophic. Steel does not bend unless it is being overloaded. Mucklow reported his findings to the site engineer, who reported them to the Quebec Bridge Company, who sent a telegram to Theodore Cooper in New York. Cooper's response was dismissive. He stated that some deflection was expected and not necessarily dangerous. He advised monitoring the situation, but did not order work to stop. Mucklow was not satisfied. On August 27th, he traveled to New York personally to meet with Cooper and show him photographs of the bending cords. Cooper reviewed the evidence and finally understood the severity. He drafted a telegram ordering all work on the bridge to stop immediately. August 27th, 1907. Norman Mucklow stood in Theodore Cooper's office in New York City, holding photographs of steel beams that should have been straight but were bent like bows. Mucklow was exhausted. He had worked a full shift on the bridge, then taken a train overnight to New York, spending his own money because he believed the bridge was about to collapse and no one with authority was listening. Cooper examined the photographs. Mucklow pointed to the images of compression cords A9L and A9R, the massive steel beams running along the underside of the south cantilever arm. The photographs showed visible curvature. The beams were bowing outward under load, a clear indication of buckling. Cooper had designed these cords to be straight under all loading conditions. The fact that they were bending meant they were being subjected to forces greater than the design anticipated. Cooper asked Mucklow how much deflection had been measured. Mucklow provided the numbers. 1 inch on August 20th, 2 inches on August 22nd, 2.5 inches on August 25th, 3 inches on August 27th. The deflection was increasing exponentially, not linearly. This was the signature of impending catastrophic failure. When a steel beam begins to buckle, the deflection accelerates as the material loses its ability to resist further bending. Cooper should have recognized this immediately. He did not. Instead, he questioned whether the measurements were accurate. He suggested that thermal expansion from sunlight might be causing temporary deformation that would reverse at night. He pointed out that the bridge had been standing for months without incident, which suggested the structure was stable. Mucklow argued that the deflection was not reversing. It was cumulative. The beams were permanently deforming. Workers on the bridge could hear the steel groaning under load, a deep metallic sound like a ship's hull under stress. Rivets were popping out of their holes as the steel twisted. The structure was screaming warnings that everyone on site could hear, but Cooper, sitting in an office 300 miles away, could not. The meeting lasted over an hour. Cooper finally agreed to send a telegram to Quebec ordering a halt to all work on the cantilever arm until a full inspection could be conducted, but he did not declare an emergency. He did not order an immediate evacuation. He framed the telegram as a precautionary measure, not an urgent safety directive. McClure left Cooper's office believing the situation was under control. He took the evening train back to Quebec, expecting to find the bridge shut down when he arrived. Meanwhile, back at the construction site, work continued. The site engineer, Peter Slapka, had received earlier telegram from Cooper expressing concern about the compression cords, but none of them explicitly ordered work to stop. Slapka interpreted Cooper's messages as advisory, not mandatory. The schedule was tight. The bridge company was under financial pressure to complete the structure before winter. Stopping work would mean delays, cost overruns, and difficult conversations with investors. Slapka made the decision to continue operations while monitoring the deflection. This decision killed 75 men. On the morning of August 29th, the compression cords were deflecting at a rate of half an inch per day. Workers reported that the steel was making popping and cracking sounds continuously. Some of the riveters, particularly the Mohawk ironworkers who made up a large portion of the crew, expressed unease. The Mohawk had a cultural tradition of working on high steel structures, and many of the most experienced bridge workers in North America were from the Conowick Reserve near Montreal. These men had worked on bridges and skyscrapers across the continent. They understood steel. Several Mohawk workers told their foreman they believed the bridge was unsafe. They were told to return to work or lose their jobs. At 3 p.m., Theodore Cooper's telegram finally arrived at the Quebec Bridge Company office. The message was clear. Stop all work on the bridge immediately. Do not add any additional load to the cantilever arm. The telegram was handed to a clerk, who was supposed to deliver it to the construction site. The site was a quarter-mile from the office. The clerk decided to finish some paperwork first and deliver the telegram at the end of his shift. By the time he walked to the bridge, it would be 5:30 p.m., nearly quitting time for the workers. There was no urgency. Meanwhile, on the bridge, the day shift was ending. 75 men were working on the south cantilever arm, completing the day's tasks. Riveters were driving the final rivets into newly installed beams. Fitters were positioning steel plates for the next day's work. Laborers were moving materials and tools. The structure extended 900 feet over the river, a latticework of steel beams and trusses held together by hundreds of thousands of rivets. At 5:35 p.m., 2 minutes before the collapse, several workers heard a loud crack, followed by a series of smaller popping sounds. One worker, David Homer, later testified that he looked down and saw a compression cord beneath his feet visibly bending, twisting like a rope being wrung out. He shouted a warning and began running toward the shore. He had taken perhaps 10 steps when the structure gave way. The failure began at the lower compression Chord A9L on the riverside of the south cantilever arm. The steel buckled suddenly, folding inward like a crushed soda can. The cord was designed to resist compression, to push back against the downward load of the cantilever. Once it buckled, it could no longer support any load. The entire weight of the cantilever arm, 19,000 tons, transferred instantaneously to the adjacent structural members, which were not designed to carry that load. They failed immediately. The collapse propagated through the structure like a zipper opening. One by one, the connecting beams and trusses buckled, twisted, and broke. The sound was described by witnesses on shore as similar to artillery fire, a rapid series of explosions as steel members fractured under stress. The entire south cantilever arm, a structure 900 feet long and weighing 19,000 tons, fell into the St. Lawrence River in 15 seconds. Men on the bridge had no time to react. Some tried to run. The structure was collapsing faster than they could move. Others grabbed onto beams as the steel twisted beneath them, holding on until the impact with the water tore them loose. A few jumped, hoping to survive the fall. The river was 50 feet below. Hitting water from that height is like hitting concrete. Workers on shore watched in horror as the massive structure folded in on itself and dropped. The impact created a wave that traveled across the river and broke against the opposite shore. Debris rained down for several minutes afterward, smaller pieces of steel and wood splashing into the water. The dust cloud from pulverized concrete and rust took nearly an hour to settle. When the air cleared, the bridge was gone. All that remained were the approach spans on shore and the twisted wreckage jutting from the river. Rescue efforts began immediately but were largely futile. The wreckage had fallen into over 60 feet of water. The steel beam formed a tangled mass on the riverbed, trapping bodies beneath tons of metal. Divers went down but could not navigate the debris. August 30th, 1907. The morning after the collapse, investigators arrived at the site to begin the grim task of understanding what had happened. The wreckage told the story clearly. The compression cords had buckled. The steel had been overloaded. But why? The Quebec Bridge Company immediately formed an internal investigation committee, but the Canadian government intervened. The disaster was too significant, the loss of life too great, to be handled by the company responsible. The federal government established a Royal Commission of Inquiry, appointing 3 of the most respected engineers in the country to lead it. The commission's mandate was simple: determine the cause of the collapse, assign responsibility, and recommend changes to prevent future disasters. The investigation lasted months. Engineers examined every piece of wreckage that could be recovered from the river. Divers brought up sections of the failed compression cords, which were analyzed in laboratories. Metallurgists tested the steel for defects and found none. The material itself was sound. The problem was not the quality of the steel. It was a design. The commission reviewed Theodore Cooper's calculations and found the error immediately. Cooper had assumed the weight of the extended bridge would increase proportionally when the span was lengthened from 1,600 to 1,800 feet. He had estimated the south cantilever arm would weigh 12 million pounds. The actual weight, based on the steel that was fabricated and installed, was approximately 20 million pounds. The difference was catastrophic. The compression cords were designed to support 12 million pounds. They were being asked to support 20 million. Steel has predictable failure mode under compression. When a slender column or beam is loaded beyond its critical buckling load, it will suddenly bend and collapse. The critical load depends on the cross-sectional area of the steel, the length of the unsupported span, and the material properties. Cooper had specified compression cords that were adequate for the lighter design. They were completely inadequate for the heavier structure that was actually built. The Commission's report, published in February 1908, was devastating. It concluded that the collapse was caused by errors in design and specifically blamed Theodore Cooper for failing to revise his calculations when the bridge span was increased. The report stated that Cooper's decision to manage the project remotely, without visiting the site, was a serious error in judgment that prevented him from recognizing the warning signs. The report also criticized the Quebec Bridge Company for allowing construction to continue despite clear evidence of structural distress. The commission found that the site engineer, Peter Slapka, had received multiple warnings about the bending compression cords but had failed to act decisively. The company's desire to stay on schedule and avoid cost overruns had overridden basic safety considerations. Theodore Cooper's career ended that day. He was 68 years old, in failing health, and now responsible for one of the deadliest engineering disasters in history. He issued a public statement accepting responsibility and expressing remorse, but he never worked as an engineer again. He lived in relative obscurity until his death in 1919, never fully recovering from the shame. The human cost was staggering and unevenly distributed. Of the 75 men who died, 35 were from the Conowick Mohawk community near Montreal. The Mohawk had a long tradition of working on high steel, and many families had multiple members working on the bridge. The disaster devastated the community. Some families lost fathers, sons, and brothers in a single afternoon. The Conowick Reserve held a mass funeral, and the community mourned for months. The disaster had a cultural impact that persisted for generations. To this day, the collapse is remembered in Conowick as a defining tragedy. The legal aftermath was complex. Families of the dead sued the Quebec Bridge Company, but Canadian law at the time limited corporate liability for workplace accidents. Most families received minimal compensation, often just a few $100s. The company avoided bankruptcy by securing additional government funding to rebuild the bridge, which was completed in 1917 after a second, smaller collapse during construction of the replacement span. But the most enduring legacy of the Quebec Bridge disaster was not legal or financial. It was cultural. In the aftermath, Canadian engineers recognized that the profession needed a mechanism to ensure that ego, ambition, and financial pressure could never again override engineering judgment. In 1922, a group of senior engineers proposed the creation of a ritual to remind every newly graduated engineer of their ethical obligations. The ritual became known as the Obligation of the Engineer, and it is administered to this day during a ceremony called the Ritual of the Calling of an Engineer. The ceremony is private, attended only by engineers. During the ritual, new graduates recite an oath pledging to practice engineering with humility, integrity, and respect for human life. They are reminded that their decisions have consequences, that errors can kill, and that no achievement is worth compromising safety. At the end of the ceremony, each graduate receives an iron ring, a small, plain band worn on the pinky finger of the working hand. The ring is made of iron, a reminder of the material that failed at Quebec. Some of the early rings were allegedly made from steel recovered from the wreckage of the bridge itself, though this claim is difficult to verify. Whether or not the rings contain steel from the Quebec Bridge, the symbolism is clear. The ring is a physical reminder that engineering is not an abstract exercise. It is a profession where mistakes have weight, where hubris kills, and where every decision must be made with the understanding that lives depend on it. The ring is worn for life. Engineers wear it while drafting plans, during construction site inspections, while signing off on designs. It is a constant tactile reminder. When an engineer picks up a pen or types on a keyboard, they feel the ring. When they shake hands, others see the ring. It is a mark of the profession and a mark of humility. The Quebec Bridge disaster changed engineering education as well. Universities began emphasizing site visits, peer review, and independent checking of calculations. The concept of a single engineer working in isolation, making decisions without oversight, became professionally unacceptable. Modern engineering projects require multiple layers of review, with independent consultants verifying designs and construction inspectors ensuring that the built structure matches the approved plans. Theodore Cooper's mistake, working from an office hundreds of miles from the site, would be impossible today. The bridge that stands today at Quebec is not Cooper's design. It is a heavier, stronger, more conservative structure, built with wider safety margins and subjected to rigorous testing before it was open to traffic. It has stood for over a century without incident. But the memory of the first bridge, the one that fell in 15 seconds, remains. There is a small monument near the site, listing the names of the 75 men who died. Visitors stop occasionally to read the names, many of them Mohawk, many of them young men in their 20s. September 11th, 1916. 9 years after the first collapse, the rebuilt Quebec Bridge was nearly complete. The new design, engineered with extreme conservatism and reviewed by independent experts, had progressed without major incident. The structure now consisted of 2 massive cantilever arms extending from anchor piers on each shore, designed to support a central suspended span that would complete the bridge. The suspended span, weighing 5,000 tons and measuring 640 feet long, had been fabricated on shore and floated into position on massive barges. The plan was to lift it into place using hydraulic jacks mounted on the cantilever arms, a delicate operation requiring precise coordination and engineering. At approximately 10:45 a.m., with the span partially raised and locked into temporary holding positions, the southwest bearing mechanism failed catastrophically. The suspended span dropped, twisted, and plunged into the St. Lawrence River, killing 13 workers. The second collapse was not caused by the same errors that destroyed the first bridge. It was caused by a different kind of failure, one that revealed how even the most rigorous engineering can be undone by a single overlooked detail. After the 1907 disaster, the Canadian government took direct control of the bridge project. The Quebec Bridge Company was dissolved, and the Department of Railways and Canals assumed responsibility. They hired a new chief engineer, Ralph Modjeski, widely regarded as one of the most competent bridge designers in North America. Modjeski had designed dozens of successful bridges, including major spans over the Mississippi River. He was known for conservative designs, thorough analysis, and meticulous attention to detail. He was everything Theodore Cooper was not. Modjeski's design for the replacement bridge increased the safety factors significantly. The compression cords were made heavier, the steel grades were higher quality, and every structural member was independently reviewed by consulting engineers before fabrication. The cantilever arms were constructed slowly and carefully, with continuous monitoring of deflections and stresses. By 1916, both cantilever arms were complete and had been load tested. They were stable. The final challenge was installing the central suspended span. This span had been fabricated in sections on the south shore, assembled into a complete unit, and floated on barges who positioned beneath the gap between the cantilever arms. The lifting operation was complex. Hydraulic jacks mounted on the cantilever arms would slowly raise the span using steel cables. As the span rose, workers would insert temporary support pins to lock it at specific elevations, allowing the jacks to be reset for the next lift. The process would repeat until the span reached its final position, at which point it would be permanently connected to the cantilever arms with riveted steel plates. The span weighed 5,000 tons. Lifting it required 8 hydraulic jacks, 4 on each cantilever arm, operating in perfect synchronization. Each jack exerted approximately 625 tons of lifting force. The jacks were controlled by a single operator who regulated the hydraulic pressure to ensure all 8 jacks lifted at the same rate. Uneven lifting would cause the span to tilt, potentially jamming the support mechanisms or overstressing the cables. The lifting began on September 9th. The operation proceeded smoothly. The span rose 5 feet, then 10 feet, then 15 feet. Workers inserted the temporary support pins. The jacks were reset, and the process continued. By the evening of September 10th, the span had been raised to a height of approximately 12 feet above the water. The jacks were locked, the span was resting securely on the temporary support pins, and work were halted for the night. On the morning of September 11th, the lifting resumed. The span was raised another 3 feet without incident. Then, at 10:45 a.m., workers heard a loud metallic grinding sound coming from the southwest corner of the span. The sound was followed by a sharp crack. The temporary support pin at the southwest bearing had sheared. The bearing itself, a massive cast steel assembly designed to transfer the weight of the span to the cantilever arm, had deformed under load. The casting had a hidden flaw, a void created during the manufacturing process when the molten steel failed to completely fill the mold. The void was internal, invisible to visual inspection, and located precisely at the point of maximum stress. When the span was lifted and the load concentrated on the bearing, the thin wall of steel surrounding the void cracked. The bearing collapsed. The southwest corner of the suspended span dropped immediately. The span, no longer supported evenly, began to tilt. The tilting caused the opposite corner, the northeast bearing, to experience a sudden increase in load as the weight shifted. The northeast bearing, which had been supporting approximately 1,250 tons, was now supporting over 3,000 tons. It held for approximately 2 seconds, then it failed as well. The span was now unsupported on one entire side. The hydraulic cables on the failed side went slack, then snapped as the tilting span pulled them at an angle they were not designed to resist. The cables whipped through the air like steel bullwhips, severing one worker's arm and killing another instantly. The span rotated approximately 30 degrees, twisting as it fell. Workers on the span had no chance to escape. Some jumped toward the cantilever arms, trying to reach solid steel before the span dropped. Most did not make it. The span hit the water at an angle, the southwest corner striking first, followed by the rest of the structure in a cascading impact that created a wave visible from shore. The entire event, from the initial crack to the final impact, lasted less than 10 seconds. 13 men died. 12 fell with the span and drowned or were crushed by the steel. 1 was killed by the snapping cable. The bodies of 3 workers were never recovered, trapped beneath the wreckage on the riverbed. The investigation began immediately. Engineers recovered the failed bearing from the river and sectioned it for metallurgical analysis. The internal void was discovered during microscopic examination. The casting had been manufactured by a reputable foundry, inspected visually before installation, and assumed to be sound. But visual inspection cannot detect internal flaws. The void was only visible when the bearing was cut open. The investigation concluded that the failure was caused by a defective casting that passed inspection due to limitations in the inspection technology available at the time. The report recommended that all future castings for critical structural components be subjected to radiographic inspection using X-rays to detect internal voids before installation. This recommendation became standard practice in bridge construction and is still used today. The psychological impact on the workers and engineers was profound. The first collapse had been attributed to arrogance and errors in judgment. It was a failure that, in hindsight, seemed preventable. The second collapse was different. The engineers had done everything right. The design was conservative. The construction was careful. The materials were high quality. And yet, 13 men still died because of an invisible flaw in a single component.